Good morning, dear students. Today, inshallah, we will start in lesson 4, which is the last lesson in this term, inshallah. In lesson 4, we will talk about the oxidation numbers, which is the last property we will study in unit 2. First, to know what is an oxidation number, we should know that it's a number that refers to the electric charge, either positive or negative charge, that the atom or the ion would carry in a compound, whether this compound is ionic or covalent compound. So, in ionic compounds, for example, the oxidation number of any atom is equal to its valency preceded by a positive sign in case of a cation, or with a negative sign in case of anions. So we can notice the sodium atom in the opposite diagram having an atomic number equals 11, which means that it has 11 protons and 11 neutrons and 11 electrons. By losing its valence electron and forming a positive ion, we can notice that the number of the protons now is still 11, but it has only 10 electrons, which means that the net charge of the ion is positive 1. So the oxidation number of sodium atom in an ionic compound is always positive 1. And the same thing applies to chlorine atom, as it has 17 protons and 17 electrons. Chlorine atom gains an extra electron to its outermost energy level, so forming a negative ion. So it's the net charge of the chloride ion is negative 1. So the oxidation number of the chloride ion is negative 1 as well. If the oxidation number is positive, this indicates that the number of electrons that the atom has lost. While if the oxidation number is negative, this indicates the number of electrons that the atom has gained. Positive charge indicates the atom which has less electronegativity, while the negative charge or the negative charge represents the atom which has less more electronegativity. So we say that the more electronegative atom in a covalent compound carries a negative charge, while the less electronegative atom carries a positive charge. We already know that in covalent compounds, in polar covalent compounds, the more electronegative atom carries a partial negative charge, while the less electronegative atom carries a partial positive charge. But to calculate the oxidation numbers, we say that the less electronegative atom carries a positive charge, while the more electronegative atom carries a negative charge. Let's talk about the rules for assigning oxidation numbers. First of all, the oxidation number of any element given in a molecule of similar atoms equals 0. So if you have a monoatomic molecule or a diatomic molecule, or even more than that, of any element, we can say that the oxidation number of this element equals 0, whatever the multiplicity of the molecule atoms, because the sharing of electrons in between the atoms of any element are always equal. So for sodium, iron, hydrogen, oxygen, ozone, phosphorus, sulfur, all of these molecules represent the molecules of elements, so their oxidation numbers equal 0 in their elemental state. Second, the oxidation number of an element ion is equal to the charge of the ion. So if you have any ion carrying a positive charge or a negative charge, then the oxidation number of the ion is equal to this charge. Then the oxidation number of polyatomic ions is equal to the charge of the atomic group. If we're talking about the ammonium ion, hydroxide ion, carbonate, phosphate, sulfate, nitrate, nitrite, any polyatomic group has a charge either positive or negative, so the oxidation number of this group is equal to the charge. Then let's talk about the oxidation number of group 1A elements, which is always equal to positive 1, group 2A elements, which is always equal to positive 2, group 3A elements, which is always equal to positive 3. The oxidation number of fluorine in all of its compounds is negative 1, and that's because the electronegativity of fluorine is greater than that of all other elements. That's why it always equals negative 1. While the oxidation number of other halogens like chlorine, bromine, and iodine in most of their compounds, especially their ionic compounds, their oxidation numbers equal negative 1. While their other oxidation numbers in other different compounds can be assigned mathematically. The oxidation number for oxygen in most of its compounds is negative 2, except for 3 types of compounds. In peroxides, the oxidation number of oxygen equals negative 1, while in superoxides, the oxidation number of oxygen equals negative half, while in oxygen difluoride, the oxidation number of oxygen equals positive 2. This is because fluorine atom is the only atom which has higher electronegativity than oxygen, and that's why oxygen is acquired a positive charge in oxygen difluoride. The oxidation number for hydrogen in most of its compounds equals positive 1, except in some compounds where it reacts with active metals, and these compounds are known as metal hydrides, in which hydrogen has an oxidation number of negative 1 because it reacts with metals which have less electronegativity or lower electronegativity than hydrogen. That's why hydrogen is acquired a negative charge. The algebraic sum of the oxidation numbers of all atoms in a neutral compound or in any given molecule must be equal 0. The algebraic sum of the oxidation numbers of all atoms in polyatomic ions must be equal to the charge of the ion. Okay, how to calculate the change in oxidation number in oxidation reduction reactions? We should note first that oxidation is the process of losing electrons, which leads to increasing the oxidation number, and reduction is the process of gaining electrons, which leads to a decrease in the oxidation number. And the reducing agent is the oxidized species, so the species which undergo oxidation process is said to be the reducing agent, while the species which undergo the reduction process is said to be the oxidizing agent. Let's have some examples. If we're asked to find the oxidized and the reduced species, mentioning the change in their oxidation numbers in a given equation. So the reaction is between potassium dichromate plus iron 2 chloride plus hydrochloric acid, forming potassium chloride and chromium 3 chloride and iron 3 chloride and water. The change in the oxidation numbers here and the oxidized and the reduced species should be known. First, we should calculate the oxidation number of each element on its own. So, for the first compound, potassium dichromate, it's known that the oxidation number of oxygen equals -2 and the oxidation number of potassium equals +1. And this is sum of the fixed oxidation numbers because potassium lies in group 1A, so it always has an oxidation number equals +1, and oxygen usually have a -2 oxidation number except in 3 compounds that we've mentioned. So we can calculate the oxidation number of chromium in the first compound, potassium dichromate. So each chromium atom will find that its oxidation number is +6. In the second compound, FeCl2, we can easily conclude or calculate the oxidation number of iron of Fe, which equals +2. We can notice in the product that the chromium atom, the oxidation number of chromium atom is +3 in chromium 3 chloride, as chlorine is a halogen which has an oxidation number equals -1. So the oxidation number of chromium here is +3, while the oxidation number of iron in FeCl3 is also +3, which means that the chromium enters the reaction or found in the reactants as with oxidation number +6 and coming out of the reaction in the products with oxidation number +3. So as long as the oxidation number decreases, so we can say that a reduction process took place. And if the reduction process took place through the chromium atom, we can say that it's said to be the oxidized species. So chromium is the oxidized or the oxidizing agent which undergo a reduction process. On the opposite side, iron Fe entered the reaction as iron +2 and found in products as iron +3. So the oxidation number increases through the reaction. The oxidation number of iron increases. So an oxidation process took place, and we can say that it is the reducing agent.